Welcome you all again for the thermodynamic lecture series. So in this today's lecture we are going to solve a few more problems on constant temperature process to find out the properties of pure substance. So before getting into the problem, so we need to know what is the state of the steam. Okay, so there is the condition of the steam or the quality of the steam we need to identify. So for that we all know that they are having three different conditions or quality of the steam is available. The first one is wet steam, and second one is dry steam, and third one is your superheated steam. Okay, so how these qualities are classified? Okay, so these classification, how these qualities are classified is detailedly explained in the previous lectures. If you have any doubt, you can go through the previous lecture. Okay, so just I am recalling that. So if we say the given specific enthalpy is lesser than the specific enthalpy of saturated vapor, then it is called as a wet steam. Okay, when a given specific enthalpy which is equal to saturated specific enthalpy of vapor, then they are called as dry steam. Okay, so here x value which is equal to 1 here. Okay, then if we say it is a superheated steam, then the specific enthalpy of the saturated vapor is lesser than your given enthalpy. Okay, so this will be applicable for your specific volume also. Okay, for instance, so the given specific volume is lesser than the saturated specific volume of the vapor, then it is called as a wet steam. When the given specific volume and the saturated specific volume of the gas which is equal, they are called as dry steam. When the saturated specific volume of the vapor which is lesser than your given specific volume, then it is called as your superheated steam. Okay, since the same condition will be applied for your specific entropy also. When coming on your temperature, we should say it is a saturation temperature. Okay, so we all know what is saturation temperature. So at this point the phase changes will occur. So in this saturation point, the given temperature is lesser than your saturation point, the steam will be of a wet steam. Then your given temperature which is equal to the saturation temperature, then it is a dry steam. Then the saturation temperature is lesser than your given temperature, then it is known as the state of the steam is your superheated steam. Then, so based on the qualities wet steam, dry steam and superheated steam, we should know some of the basic properties and how to use the formulas for your basic properties. Okay, so first one is your specific enthalpy, the unit is kilojoule per kilogram. If we say the steam is wet, the condition is the given specific enthalpy is lesser than that of your saturated specific enthalpy, then H is equal to HF plus X into HFG. Okay, where H is your specific enthalpy at liquid stage. Okay, so this is your combination of both, so liquid and gaseous vapor. Okay, so X is nothing but your dryness fraction. Okay, what is meant by dryness fraction? That is the amount of, that is the mass of vapor present in the total amount of the steam. Okay, so that is mg by mf plus mg. Okay, X equal to mg by mf plus mg. Then if we say dry steam, I already told that X equal to 1. You substitute your X equal to 1, then it becomes HFG. Okay, so HFG can be written as Hg minus HF. So plus HF and minus HF will get cancelled. Again the term will be H is equal to Hg here. For superheated, so H is equal to Hg plus Cp, that is the constant pressure of the superheated temperature values. Then your T superheated minus your T saturation temperature, the difference between your superheated and saturation temperature. For specific volume, again for a wet condition, V is equal to Vf plus X into Vfg, and for dry steam it is V is equal to Vg, and for superheated steam V is equal to Vg into T sup by T saturation. And also for your specific entropy, S is equal to Sf plus X into Sfg, where S equal to Sg. Here for superheated, S is equal to Sg plus Cps of log into the ratio of T sup by superheated temperature divided by your saturation temperature. And also work done. So we also know that the flow work is equal to P into V. So that is work done is equal to P into V for all the three cases. But this volume, the specific volume will be varied according to these three different conditions. And also know the specific volume is instead of the reciprocal of your density, or otherwise density can be written as 1 by your specific volume in all the three cases of your quality of the steam. Then the specific internal can be determined by H is equal to U plus PV relation, So with this we can write U, specific internal energy U is equal to H minus PV. So this H, the specific enthalpy and the specific volume will be depend on these formulas. What are all the state of the conditions? So corresponding state of the conditions, the signal energy will vary, but the formula for the internal energy for all the three cases are same. Okay. Problem 16. A steam at 30 bar and 350 degrees Celsius is expanded in a non-flow isothermal process. Okay. So here, clearly it has stated that the steam at the initial pressure P1 is equal to 30 bar and the initial temperature T1 is 350 degrees Celsius, it is expanding. Okay. So how it is expanding? So it is in a non-flow process. That non-flow process is also in the type of your constant temperature. That is your isothermal process. So we can write T1 is equal to T2 to a pressure of 1 bar. Okay. So P2 is equal to 1 bar. The temperature and the pressure, the surrounding temperatures are given. So it is mentioned as P0 and T0. Okay. So T0 is 25 degrees Celsius and P0 is 100 kilopascal respectively. Determine the maximum work that can be obtained from this process per kg of steam. Okay. And also find out the maximum useful work. So here we need to find out the work done, and also we need to find out your maximum useful work by your availability analysis. So from pressure P1 is equal to 30 bar, so we have to take your saturation temperature. So here the saturation temperature is 233.8 degrees Celsius. You compare with the given temperature. So given temperature is 350 degrees Celsius. So the saturation temperature is lesser than given temperature. So the condition of the steam is superheated here, right? Then from your superheated steam table at pressure P1 is equal to 30 bar and T1 is equal to 350 degree Celsius. So pressure P1 is equal to 30 bar and temperature is 350 degrees Celsius. So you can take the specific volume B1 is 0.09053 meter cube per kilo. And again from your steam table, specific enthalpy of the superheated steam table. So you apply the pressure 30 bar and temperature T1 is equal to 350 degrees Celsius. So you can take the values of this H1, specific enthalpy. H1 is 3117.5 kilojoule per kilogram. Then we need to take the specific entropy, that is also the superheated condition. So at the specific entropy of superheated steam table at pressure P1 is equal to 30 bar and temperature T1 is equal to 350 degrees Celsius, the specific entropy S1 is 6.747 kilojoule per kilogram Kelvin. Then U1 is H1 minus P1 V1. So you substitute this H1 and V1. This P1 will be substituted in terms of kilopascal. So this is very careful. You have to substitute this value. Then you will get the specific internal energy U1 is equal to 2845.91 kilojoule per kilogram. Since the process is of isothermal process, so we can say it is T1 is equal to T2, right? So for that, the given condition P2 is 1 bar is given for the second state. So we can compare the pressure and temperature and we can find out the state of the steam in your second condition. So at 1 bar pressure, the temperature, saturation temperature is 99.63 degrees Celsius, but given that T1 is equal to 350 degrees Celsius, since it is an isothermal or constant temperature process, so T1 which is equal to T2 is 350 degrees Celsius, so 99.63 is lesser than, that is 350. T saturation is lesser than T2 here, so the condition of the steam is again superheated at the state 2. So again you go for your superheated steam table at the pressure P1 is equal to 1 bar and temperature is equal to 350 degrees Celsius. You can take V2 is equal to 2.871 meter cube per kilogram. And in the similar way you can go for your specific enthalpy of your superheated steam table at pressure P1 is equal to 1 bar and the temperature T2 is equal to 350 degrees Celsius. You can take H2 is equal to 3175.6 kilojoule per kilogram. Again you go for the superheated steam table for finding out your specific entropy. So at the pressure P2 is equal to 1 bar and the temperature T2 is equal to 350 degrees Celsius, you can take the specific entropy of 8.386 kilojoule per kilogram Kelvin. And you are going to find out the U2. So U2 is H2 minus P2 V2. So H2 we know, P2 you have to substitute in terms of kilopascal. You will get U2 is 288.5 kilojoule per kilogram. So as a result, you need to find out the work transfer, right? So from the first law of thermodynamics, Q is equal to W plus del U. Since it is a constant temperature process, so delta U is equal to 0 because MCP into T2 minus T1, where T1 which is equal to T2, so we can neglect this term. Okay, so delta U is equal to 0 here. So Q is equal to W. So as we all know, the formula for Q in a constant temperature process we have discussed in the previous lecture. So if you have any doubt, you go for the constant temperature process derivation, that also we have posted. Okay, so you and check it out. Then Q is equal to P1 V1 ln of P1 by P2. You substitute all those values, substitute the values in terms of kilopascal here. Okay, so this value will be of kilopascal. Okay, so V1 we already know, so you substitute those values to get Q is equal to W is equal to 923.73 kilojoule per kilogram. But we need to find out, this is your work and maximum work we need to find out. For that we are going for your availability analysis. So since it is a closed system, so we can take W max equal to psi1 minus psi2. Okay, phi1 minus phi2. So again this formula can be written as work done of max into U1 minus U2 minus T0 into S1 minus S2 plus P0 into V1 minus V2. Here we have to consider your ambient conditions also. Okay, so substitute all those values here to get the work done of max, which is equal to 167.785 kilojoule per kilogram. So as a result, the work done is 923.73 kilojoule per kilogram, but the maximum useful work done maximum is 167.785 kilojoule per kilogram. Thank you.